Okay, let's look at another type of reaction, combustion reactions, which you're all probably familiar with, but now let's look at the science behind some of them. And predominantly when we deal with combustion reactions, we're talking about the burning of hydrocarbons, and we'll do a topic called hydrocarbons later in the year, but we'll just throw this at you right now just so that you can do this type of reaction. Now, a hydrocarbon is a compound that only consists predominantly of hydrogen and carbon, maybe some other things, but hydrogen and carbon. And when they burn in air, because they're only consisting of hydrogen and carbon, and they're burning in air, the part they're using in air is of course the oxygen, you can only get carbon dioxide and water as the products. And so they're fairly simple like that. And so let's do an example. Now, there's a hydrocarbon called octane, which you may have heard about. It's got the formula C8H18. You're burning it in air, and so we just need to reinforce the fact that when we're talking air, we're talking about oxygen, O2. Nothing else in the air is actually involved in burning. And burning or combustion is effectively an oxidization process, but we don't say that. The combustion may be represented as, let's have a look. Here we go. Now, here's your octane, there's your oxygen, there's your carbon dioxide and water, and then they've actually balanced it out. And you can see that because we're starting off with so many carbons and hydrogens, the actual process of balancing it ends up with some large numbers, and that's not uncommon. And that's where using, if you can remember, the half technique to get that final balance. And then once you use a half, you then multiply everything, and that gives you the coefficients that you need to balance the equation. And you'll have a go at doing some of these. Now, we also present you with the situations where we're burning or we're doing combustion, but the oxygen supply is limited. And as a result, instead of getting carbon dioxide, we get carbon monoxide, which is just CO. So the burning is not as complete or not as efficient. And that happens in a car. It happens when you have your wood heater at home and you turn it down at night and smoke comes out the chimney. That's inefficient burning, and it's burning when the oxygen is limited as to how much you have. So what does that look like? Well, it doesn't change the way we do it. So you just got to recognize you still got oxygen, still burning, still got the octane, but instead of carbon dioxide you're producing carbon monoxide. And that's actually more poisonous than carbon dioxide. Carbon dioxide will kill you if you're burning in a closed room, but it's the carbon monoxide that knocks you out real quick if you're burning. And people who have tried heating their homes with barbecues, or have gone camping and built a snow cave without adequate ventilation, can actually poison themselves with the carbon monoxide. It basically puts you to sleep very quickly before you realize that you're actually being poisoned, and then you asphyxiate yourself. But again, big coefficients required to balance the equation, so they're good practice at balancing these equations. Now, I did mention that you could also get one other product that you might get from inefficient burning is this guy, which is solid carbon, more commonly known as soot. And so you might be given a question where, say, a candle is burning and someone observes that the candle is giving off smoke. What's the equation for that? And you would include carbon as it. But if it's just limited oxygen and there's no other clue as to there being any smoke or soot or anything, you just put carbon monoxide and water. Alright, and I'll demonstrate that to you in class, and you'll have a go at doing these questions in class as well. Let's just go back one, and I'll also make sure We haven't done this yet, so these are the formulas for propane, ethene and ethane, and when we do hydrocarbons you'll understand where those names come from and you'll be able to do it yourself. Okay, and in our next video, which I think may be the last in chemical reactions, we're going to look at dissociation reactions and we'll revisit ionic equations, which we talked about earlier. Alright, cheerio.